Hello everyone. So today we're going to start talking, excuse me, today we're going to start talking about graph algorithms, which is going to be important to us for Project 4. And there's other lectures that are going to be part of Project 4 also, but this is the initial lead-in that's going to set things up. So when we talk about a graph, we've got a collection of vertices and edges. And if we have these two things, we have a graph, and we can also describe each edge as a set of size 2. So each edge could be a pair of vertices that are connected by an edge. So is this a graph? Sure, it's a tree. It's a graph that doesn't have any cycles, and although we don't show any arrows here, we tend to think of a tree as having arrows that point downward, but they don't have to. They could be bidirectional. They could point both up and down. What about this? Is this a graph? Well, it's got vertices, it's got edges, so yeah, I suppose that's a graph also. It's a disconnected graph. There's two regions to the graph. There's this region that's not connected to the other part. And the larger part has regions that are it has vertices that are connected to themselves. It has vertices that are connected by two different edges, but it still meets our definition of a graph. It's a collection of vertices and edges. Now, in general, when we say graph, it is allowed to have parallel edges. Parallel edges would be what we had in the previous slide, going from 17 to 50. And it's also allowed to have a self loop, which is the 48 connecting to itself. So in general, graphs allow those. However, when we have a graph that doesn't have either one of those, if we don't have parallel edges, if we don't have self loops, then that's referred to as a simple graph. And from now on, rest of the semester, if we say graph, unless we say otherwise, we mean simple graph. So those extra edges would complicate both some algorithms and our analysis of the algorithms on those graphs. So for instance, if I said, oh, what's the complexity of this algorithm? You say, oh, it's O of the number of edges. I say, well, if you allow parallel edges, then the number of edges could be infinite. You know, you've only got 4 vertices, but I can have an infinite number of edges going from A to B. So then the complexity is infinite on a graph with only 4 vertices. So that's why, in general, when we say graph, we mean a simple graph, so that we can get a better limit on the number of edges. Okay, is this a simple graph? No, it's got that cycle from 48 back to itself. So if we take that out, is it a simple graph? Yes, it's not connected. There are places like 50 that you can't get to if you're at 62, but it is a simple graph. So it's a simple graph that happens to be disconnected. It has two regions that have no edges between them. So we can talk about a simple path. So a simple path is a sequence of edges leading from one vertex to another. Oh wait, I just had to pause for a second there. I saw my preview window was giving me the swirling cursor on my preview. Okay, so if we have a simple path, we've got a sequence of edges which lead from one vertex to another, and no vertex appears twice. So the word simple is used in the same sense here, that you can't get there in two different ways, in that they aren't both in, you don't have something repeated in the path. In a connected graph, we could have a simple path exists between any pair of vertices, and any here may sound odd. Maybe a better word would be every. What it means is if you pick any pair of vertices, there is a simple path connecting them. So we could also say between every pair of vertices, there exists a simple path. Now we might also have cycles in our graph. There might be a simple path except the first and final nodes are the same. So I could go from A to B to C and back to A. That would be a cycle. And our graph could contain cycles. It doesn't mean that we must have only one simple path between any pair of vertices. We could have multiple paths. It's just that there must be at least one path between any pair of vertices for it to be a connected graph. So a cycle is this simple path where we repeat the first and last nodes. And we could also have some characteristics of the graph itself, not just what we're doing with it. We could have a directed graph, also referred to as a digraph, where edges have one direction. And so we could have an ordered pair. UV means there is an edge from U to V. And if we have a directed graph, and I have, let's just use the same letters, I have U and V, I could have an edge there and an edge there, and that would not be considered parallel edges because they don't duplicate the path that you can take. So you can go from U to V, you can also follow a different edge to go from V to U. This is still a simple graph because those are not parallel edges, they go in different directions. So that would be allowed and still be a simple graph. So in a directed graph, every edge has a directionality. In an undirected graph, the order of the vertices that we list in an edge isn't important. So when I say there's an edge U comma V, it means there is an edge between those two vertices and you can traverse it in either direction. So, when you're looking at a list of edges described by which vertices they connect, it's important to know up front, are we talking about a directed graph or an undirected graph? When we look at it, it's easy to see. If there are arrows in it, it's a directed graph, and if there are no arrows, it's an undirected graph. And it would be possible, I've seen sometimes where a directed graph might be drawn a couple of different ways. We might say, oh, there's an edge from 3 to 4, and there's also an edge from 4 to 3. It might also be drawn as the edge from 2 to 4 has arrows on both ends. So I've seen them presented both ways. It tends to be, say, a given textbook or research paper will choose a representation and be consistent throughout. So it's just important to understand if you look at other sources and for examples and descriptions of graphs, just be aware that it could be presented either way. Another characteristic that we could have on a graph is that the edges could have a weight. And we put that in quote marks there because every term that we use here has some connotation. It makes you think of something else. So if I say weight, then you think, well, does it mean pounds or kilograms? And if I say cost, you think, does it mean dollars or euros or pounds or yen? So any word that we use has a connotation associated with it. But the real meaning is that there's a number associated with each edge, and if we had an algorithm where we were trying to, say, minimize the total sum of those values or maximize the total sum of those values, we could have different algorithms that would be working on those. And it really, the term might depend upon the problem that we're trying to solve. So we might call it a distance, which could be miles or kilometers. And then we could say, we're trying to minimize the total distance. So if we say weight or cost or distance, we all mean basically the same thing, that there's a number associated with each edge. And if we're presenting those numbers, it probably means that there's going to be an algorithm coming up applied to that graph where we want to minimize or maximize those the sum of those values that are selected to solve the problem. And we're going to have some examples of different problems coming up. And many times we want to minimize those if we're talking like cost in terms of dollars or miles traveled. Usually people want to minimize those things. But there's also other graph algorithms where we are going to try to maximize them. So, given this graph, would you say that it is directed or undirected? Would you say it's weighted or unweighted? Well, if we take a quick look at the graph, and we're going to be seeing this graph coming up throughout lecture today, if we look through this graph, I can say, I don't see any arrows on the end of any edge that I've noticed. So it looks like it's an undirected graph, and it looks like there's a number associated with every edge, so that looks like a weighted graph. So it looks here like we've got an undirected weighted graph. And you could list them in any order. You could say it's undirected weighted graph. You could say it's a weighted undirected graph. And as long as you list them, the order doesn't matter. So when we talk about graphs, we're also going to come up against a couple examples today of board games, because many board games involve graphs. There's an example here of a game called Ticket to Ride, and there's Ticket to Ride US, there's Ticket to Ride Europe, etc. And trying to think if Asia is in the Europe one, because I remember building a line from Paris to Siberia when I played Ticket to Ride Europe, but I can't remember if Europe is officially part of Asia or Europe. Anyway, so there's lots of board games that involve graphs and connecting things. Some are more explicit than others. This one, very clearly, there are railroad lines connecting different cities. Other games you might think of, well, Monopoly. People don't think of Monopoly as having a connected graph, but you can go from, you always travel clockwise, and you can get from the location you are on to any location that follows by adding the roll of die or dice. Wow, it's been a while since I played Monopoly. I think you roll 2 dice, but that seems like you get around the board really quickly. Can't remember, but dice rolls determine where you go from here, but you can reach from this location that you're at. You can reach any location going clockwise that is reachable with the total faces of the number of dice. Okay, thank you, Jacob. 2 dice. I just haven't played Monopoly in forever. I've been playing more modern games than that, like Ticket to Ride, Catan, Dominion, stuff like that. So some games very clearly have a graph, some indirectly have a graph, and some games really don't have a graph associated with them, but many do. So we're going to look at some graph implementations. How do we represent a graph? So we could say, I have a complete graph. In a complete graph, we have our list of edges. Well, the number of edges is equal to the number of vertices times number of vertices minus 1 divided by 2, which is approximately equal to the number of vertices squared. Now, very often, you're going to see that we're going to leave the vertical bars off. So if you see things like E times V or V squared, it generally means V is being used to represent the number of vertices rather than the set of all vertices. So we will sometimes in our slides get a little bit sloppy and say things like E is approximately equal to V squared, when really what we mean is the size of the set of E is approximately equal to the size of the set V, the quantity squared. So we can write it either way. We just have to understand that to be rigorous, we should put the vertical bars to say size of the set, but we often don't for convenience sake. So when we talk about a graph, before we talk about the actual representations, the representation is going to really depend on whether we have a dense graph or a sparse graph. So the most dense graph possible Every possible edge exists, and since we haven't said otherwise, we have to assume that we're talking about simple graphs here. So since these are simple graphs, the number of edges is at most v times v minus 1 over 2. So that's a complete graph. Every possible edge exists. In a dense graph, it says E is proportional to v squared. What we're saying here is not an exact line. It's impossible to take the set of all graphs and say, here is the line between dense and sparse. But in a dense graph, E will be proportional to v squared. In a sparse graph, E will be proportional to v, or another way to say it here is E is much less than v squared. Not E gets its output redirected from v squared, it means E is much less than v squared. So if E is much less than v squared, or E is proportional to v, then we would say that the list is sparse. And if E is closer to v squared than it is to v, then we would say that it's a dense graph. So there is no fixed line between them. What I would do is I would say, well, let's look at the algorithm that we're going to use. Let's look at what its complexity would be, and let's decide for a given graph whether this graph is dense or sparse based on really what it would do to our complexity. If we do the dense representation and the dense algorithm, then what is our complexity on this graph, and what is it if we do it as sparse? But generally, for our projects, we're going to let you know. We're going to let you know up front, or we're going to let you figure it out from clues that we provide in the spec, which representation is going to be important. But in Project 4, you only need one representation, you only need one algorithm, you don't have to implement both and then decide which one to do, etc. So you just have to look at what has to be done and what is the data that we're operating on and decide, hey, is this dense or is it sparse? And if you can't decide, there's probably hints in the video for the project. Or you could come to office hours. So we've got an example here of a graph with 5 vertices. If it's got 5 vertices, then a complete graph would have 10 edges. The dense graph, it looks like we removed, looks like 1, 2 edges there. Looks like we removed the edge from 1 to 3 and the edge from 1 to 5. So still pretty dense. And then the sparse graph here is in fact, in this one, E happens to be equal to v minus 1, which is the bare minimum number of edges to make it connected. Now, we could have the bare minimum number of edges, and like let's say I get rid of that one and I add that one, I still have a sparse graph, but it's disconnected. But if we have the right edges in our graph and we have v minus 1 edges, we can have a connected graph. And that's as sparse as it can be and still be connected. If we had less edges than that, it would, by definition, it would have to be disconnected. But it would still be a sparse graph. I'm drawing with my finger. Okay, so given this graph, would we say it's complete? Is it dense or is it sparse? Well, I don't have edges from lots of vertices to lots of others. Like 17 is only connected to one, 48, 54, 68, they're all only connected to one other vertex. So this looks pretty sparse. In fact, it is a tree. A tree is a graph with no cycles, and a connected graph with no cycles. A tree, by definition, is sparse. It's got the minimum number of edges to still be connected. Now, how do we represent our graph? One possible way to represent a graph is with an adjacency matrix. Now, in the adjacency matrix, we list basically connections that do or do not exist. Now here I've drawn it with I've filled the table with the numbers 1 or 0 to represent yes, there is an edge, and or no, there isn't. So 1 here represents true and 0 is false. When I tried doing an update on this table to change all of the zeros to lowercase false and all of the ones to lowercase true, it was harder to tell what was going on. It was harder to look at the graph and see what was connected to what, because the true and false were so filling the boxes that it was hard to tell. So I went with 0 and 1 here because it was easier for me to see. I suppose if it was somebody else, they would have thought, ooh, let's fill it with true and false, but make them different colors. But being colorblind, that is not my go-to solution for things. So we've got our graph at the bottom. We've got an adjacency matrix at the top, where a 1 means these things are adjacent, 0 means they are not. And you might say, hey, you've got an undirected graph here. Couldn't we eliminate half of this distance matrix, or sorry, half of this adjacency matrix? Since everything's symmetric, couldn't we just get rid of like the top half? And hey, I know it's a simple graph, so couldn't we eliminate not just the top half, but couldn't we eliminate the diagonal also and save space? We could cut our space requirements in half, but then we make our algorithm more complicated because I have to decide if I want to know, can I go from Dallas-Fort Worth to Boston? So DFW is Dallas-Fort Worth, BOS is Boston. I say, can I go from Dallas-Fort Worth to Boston? You say, okay, well, let me look in the Dallas-Fort Worth row. The Boston column doesn't exist. I've got to look it up in the opposite order from what you asked. So that adds an extra if and else and 2 different lookups and would actually slow us down slightly. Personally, I'd rather go for it uses twice as much memory. It's a constant amount, right? It's a constant amount of memory or a constant amount of time. Generally, I'd rather give up a constant amount of memory if I can save a constant amount of time. And also the convenience of just representation. So it's easy to represent this with a one-dimensional, with a filled square or just a triangle, but it's easier if we have the whole square graph filled in, makes things easier. We could also, we could choose to represent our graph as an adjacency matrix. We could also say, well, wait a minute, what about all the numbers? Well, we could put in zeros and numbers. So I just changed the 1s from meaning true to the cost or distance or whatever that is. Is it dollars? Is it miles? I don't know. Whatever the numbers are, I can put those in there. Now, if I say things like if LAX, if distance matrix, row LAX, column Boston, if I do an if with that, well, then that if would be false, and I would say, oh, you can't connect those. But if I'm doing an algorithm where I'm trying to minimize things, I might consider, hey, that connection from LAX to Boston is awesome. I can travel from the West Coast to the East Coast at a cost of 0 miles or $0. That looks awesome. So maybe 0 isn't the best thing to leave in there. It's easy to go from 0 false 1 true to 0 false any value is true, but it doesn't make for good minimization or maximization. So we'll get back to how we solve that problem in a second. We could also represent our graph as an adjacency list. So in the adjacency list, it's really a collection of lists. So we have a collection of lists where each list says where you can get to from here. And it is listing where you can go in one hop. So what this is saying is if you start at SFO, you can go to any one of these. You could go to LAX or DFW or Orlando or Boston. You can make any one of those four. It doesn't mean you have to go in the order listed. It just means this is the order that we listed them in. Starting at SFO in orange, you can reach any of the blue ones. And really, we would need a larger one. The ... here is meant to show that, with this example of the adjacency list, we couldn't quite fit it all in one slide and still be at a font size that was readable. So we found if we tried to put all 7 in here, it got a little bit too small. So you could imagine filling in the rest of this set of adjacency lists. And we could think of it really as like a vector of linked lists. So we find the right entry in the vector, and then we decide, hey, it's connected to each of the things in the linked list. Now, why would we choose to do the adjacency list or the adjacency matrix? Depends really on, is the graph dense or is it sparse? So if the graph is really dense, we would find that the matrix is easier to deal with. Whereas if the graph is sparse, the adjacency list might be easier and also might give us a better complexity on our algorithms. And we'll see that coming up soon when we look at different, excuse me, when we look at different algorithms and the complexities, that really it's not so much that a dense graph or sparse graph makes the algorithm a different complexity. It's the implementation, the underlying representation of the graph that allows us to step through in a different complexity. Now it says at the bottom, there's a note, it says that if we wanted to, the adjacency list nodes could contain, so each node here, each of the blue ones, we could put not just, I'm just going to get rid of the numbers there. So instead of SFO LAX just being a box that's showing the connection exists, we could also put the number in there, which is a little small on mine. I think it's 327. So we could put a number in each of those boxes also to say, hey, this is the number, the cost, the distance, whatever it is associated with that connection from SFO to LAX. And then SFO to DFW would have a different value. I think it's 1464, etc. So we could go through the whole adjacency list and make it a distance list by putting a distance in each of those. Now, like I said before, when we've got an adjacency matrix, we can make the full V by V matrix, and if we had a directed, we would have to know what to and from means. Like I might make the decision that from becomes the rows, and where you can go to is the columns. And I would make that decision up front, and I would have to put it like in my comments and make sure that I was consistent throughout, that I used it in the right way. Now, if we have a directed graph, we have to have the full V by V. We can't cut out anything if we have the matrix. Now, in the undirected, we could cut out half of it if we wanted to, but I think it's easier to just leave it the full square all the way. Now, with the weighted versus unweighted, with the unweighted, it was easy to put 0 and 1 to say there's no connection, there is a connection. There's no edge, there is an edge. However, with the weighted graph, it might be better if we said, oh, no edge, the cost is infinity because you just can't traverse it. And so that would also help make algorithms that need to minimize or maximize things easier to write. I don't have to say, if it's greater than 0, consider it, otherwise ignore it. I could just write my algorithm, and the algorithm will avoid picking anything that's infinity because it doesn't minimize very well. So, and I've got infinity plus infinity, or 5 plus 3, or better yet, 5 plus 3 or 5 plus infinity. I think I'll pick 5 plus 3. That minimizes the value. So a lot of times our algorithms don't even need special ifs to say if there's infinity in there. If we do things right, then the infinity takes care of itself. And we're going to get to how to represent that in code in a few minutes in C++. So our updated distance matrix here has infinity on the diagonals because it's a simple graph. It doesn't allow self-edges, and anywhere there is a lack of a connection between two locations like SFO and MIA, San Francisco and Miami. So there's no connection from San Francisco to Miami. There's an infinity distance associated with that. And I think we got about 1 or 2 more slides before we get to the how to do that in C++. Oh, wait, okay, 1 slide. I misremembered the number. I think it was 29. Okay, so in C++, if we include the library called limits, then there is something called numeric limits of type : thing, and it's usually thing parentheses. So for instance, we could do like numeric limits int : max. See, integers have a max and a min, and it would tell us probably 4 billion is the maximum and negative 4 billion is the minimum, or sorry, 2 billion, sorry. 2 billion is the maximum, negative 2 billion is the minimum. If we did unsigned int or uint32, the max would be 4 billion, the min would be 0. Now, not every type has an infinity. And in fact, there is something called : has, I think it has underscore infinity. And I believe has infinity doesn't have parentheses associated with it. I'm pretty sure. So has infinity will tell you, like, does this type have an infinity representation or not? So if it says has infinity is false, it still has infinity parentheses, but it's no different from max. So like if you do numeric limits of int infinity, it's the same value as numeric limits of int max. It's 2 billion. And the problem is if you take like 5 plus 2 billion, you get negative 2 billion-ish. And it wraps around. So whereas if a type like double or float are the only two that I can think of that have a special representation of infinity, if you take infinity, double infinity, and you add a finite value to it or multiply a finite value by it, you still get infinity. And in G++, things make more sense. I don't know. I didn't test all of these with Clang, with the LLVM compiler, but I tested them with what I had available, which was G++ and Visual Studio. And I think Visual Studio did a bad job here. So if you multiply 0 by infinity, Visual Studio says that's 0. G++ says it's not a number. And so that actually double has a couple of special representation for things like infinity, negative infinity, not a number, etc. So for the things that we would want to do, which is basically things like, hey, taking a value and adding infinity to it and saying, hey, let's compare this infinity to another value, it'll work out fine in either one of the compilers. So, for example, when we get to Project 4, it's really easy to just leave things as infinity and say, I'm just trying to minimize. And so, a value plus infinity, that's going to be worse than value plus another value. And it'll work out. So usually we don't do any of the things that would produce the Visual Studio and G++ to give different results. So if we can, we want to use a numeric type that has an infinity, like float or double. And then when we use that in infinity, then we can write the code more simply, and we can actually have a representation of infinity. Okay, so going back to graphs, so when I have an adjacency list, I would have a assumption. my assumption is kind of like our assumption that we made for hash tables, is that we're going to get a random distribution, and it's not going to be like, hey, this one edge has all the connections, or sorry, this one vertex has all the connections and nobody else has one. What we assume is that if there's E edges and V vertices, that there should be approximately proportional to E divided by V edges in each list. And we're going to make one assumption that accessing a particular list is O of 1. Just to get to the head of that list is O of 1. And you say, well, wait a minute, doesn't that thing have like SFOs and LAXs? Well, maybe instead of this being a vector, maybe this thing is a hash table of linked lists. And then we could assume that I can get average case O of 1 lookup to get to the head of that linked list. Okay, so that's how we could do it. We could either have vertices whose names are 0, 1, 2, 3, and that's actually what we're going to do in project 4. We're just going to make things easy and say, hey, every vertex, the name of the vertex is its index, 0, 1, 2, 3, 4, etc. So whether we have 0, 1, 2, 3, 4, or we have vertices or nodes have names, we could use a hash table to get O of 1 lookup. And then it says, so I can get to the head of the linked list in O of 1 time, and then to say, hey, does this edge exist in this vertex list? So if I go to SFO, I can get to the head of the SFO list in O of 1 time, and I want to know, is Miami in that list? It would take me time O of E divided by V. So because that's approximately how many edges there are per linked list on average, then that's how long it would take to traverse that linked list is O of E divided by V. So we would say the average cost for an individual vertex to get to the head of the linked list and to traverse the whole linked list would be O of 1 plus E over V. And if I say, well, what if I want to visit everything? I just want to take the representation. I want to take my adjacency list and I want to print out everywhere that you can get to from anywhere. So I say, I want to be able to say things like, okay, from SFO, you can get to these cities. From Miami, you can get to these cities. From Boston, you can get to these cities. And I want to print it out. Well, it would take me O of V time to get to the head of all the linked lists. And that's the total. And for every one of those, once I get to it, it's O of 1 plus E divided by V, which gives me O of V plus E. Now you say, well, why did we leave that 1 plus in there? Couldn't we have gotten rid of it? We could have, and would we have had the same complexity? Well, O of V plus E. Well, if it's an adjacency list, then the E is proportional to V. So then we would get O of V plus V, or just O of E. Either way, O of E, O of V, O of V plus V, it's all the same because E is proportional to V if we make the assumption that if you gave me an adjacency list, it better be a sparse graph, otherwise you're using the wrong representation. So yeah, we would get the same complexity, O of V. But we put it in there to remind ourselves what we had to do. I had to get to the head of the linked list, then I had to traverse that linked list. So when we look at the actual cost, it's really not. The E divided by V is approximation. It also depends on whether we have an undirected or directed graph. So in the adjacency list, in a directed graph, every adjacency list contains each edge once in the set of all edges. In an undirected graph, every one is in there twice. And we can go, we're going to look at an example on the next slide. Let's just skip over here to see. When I say, hey, SFO has ORD in it, and ORD has SFO in it. So everybody is in here twice. If we look at the original graph, there were 13 edges, I believe. I just did a quick count here. So I see 26 things in the adjacency list. But there, if we look back at the original graph, there were only 13 edges, but everybody has to be in here twice, because I can go from SFO to ORD, I can go from ORD to SFO. So that's what we meant by it appears twice in the edge set. In the set of all edges and the set of all linked lists, everybody's in there twice. Every edge from the original graph appears twice in the list of all possible places you can get from to. So in an undirected graph, everything's in there twice. So really we could go back to this and say, hey, if it's an undirected graph, it's approximately 2e over v, and we'd get a 2e in the end equation, but it's a constant factor. Our big O would still be the same. So whether it's e divided by v or 2e divided by v, we still get the same complexity in the end. Okay, so in a directed versus undirected, we would have every edge appears either once in the edge set or twice in the set of all edges. With the unweighted versus weighted, though, it's really easy. In an unweighted graph, there's no edge. Otherwise, there's a list item that has a value associated with it. Or sorry, in an unweighted graph, if there's nothing there, there's no edge, and if there is something there, there is an edge. In the weighted graph, if there's nothing there, there's no edge. We just don't represent it. However, if there's a list item with a value there, there is an edge, and that value is the cost or the weight of that edge. So in the adjacency list, we don't need an infinity. We just don't list the ones that have a cost of infinity. That's how we cut down on the amount of space, is by, hey, some of these have 4 entries. Really, if it was a complete graph, every one of these, there are 7 linked lists. Every linked list would have to have 6 items. So you'd say, wow, this looks kind of dense. They're all the same length almost, but the number of edges could have been higher. It could have been 7 times 7 is there could have been 21 edges in a graph with 7 vertices and undirected. There could have been 21 edges. We had 13. So was 13, was it dense? Was it sparse? Wow, I would say that one's in the range of hard to tell. If it's really 13 out of 21, is that dense or sparse? I could go either way on that. And the O of 1 access to a vertex list, like we said, that could be a hash table over on the left. Okay, so what about algorithms? So now we've got our ideas, we've got our representations. What are we going to do with things now? So when we look at overall complexity, we might say that the complexity is defined in terms of the number of edges, the number of vertices, or it could be both. Like we just had one there where I said, hey, if I want to list all of the edges in this list, and I just want to print out where you can get to from your starting point, it would take me O of v plus e time. So some algorithms are going to have 2 variables in their complexity. So what we've got here is we've got a few questions to think about. So we've got both representations here, and if you're looking at the slides, it's animated, it's got all the answers in it, but we want to think about these for a minute. So I want to know whether a nonstop flight from X to Y exists. So I give you 2 cities, X, Y. You have to determine, does a nonstop flight exist, and what would its complexity be for either one of the representations. And we want best, worst, best, and average for both these representations. So let's think about it. If I've got an adjacency matrix and I want to know X, Y, well, assuming that I can I can turn like Orlando into a row number, or Boston into a column number in O of 1 time, if I can do that, if I can turn the city name into an index in O of 1 time, then it only takes me O of 1 time to find the row, find the column, and determine, hey, is there an infinity there or not? Because if there's a number there, there is a connection, and if there isn't, if there's an infinity there, there's no connection. So worst case, best case, average case is O of 1. As long as I can turn the city name into a number, into an index in O of 1 time, I can do all of those things in O of 1 time. Now let's look at the adjacency list. So if I say, hey, I want to know if I can get from SFO to Boston. Well, we already assume we can get to the head of the SFO linked list in O of 1 time, but then in the worst case, I would have to traverse that whole linked list, and it could be all the way up to O of V to traverse that linked list. And I could have said O of 1 plus V, same as O of V. So it takes me O of 1 time to get to the head of the SFO list, but I might have to traverse the whole list to find that Boston is the last one, and that list could be, even in a sparse graph, there might be one node that's connected to everybody, right? I could have a graph where I've got a center and everything else is like a starfish coming off of it. And in fact, there used to be a computer network built that way. Or actually, I should say, modern networks are built that way, where there's one point that connects to everybody else, assuming we're not doing Wi-Fi. But still, Wi-Fi, same idea. I connect to the router everybody that's close to this router connects to the same router. So we could have one like that, where even though it's a sparse graph, there is someone who's connected to everybody. So I could have worst case O of V. My best case, I could have asked about, instead of SFO to BOS, I could have asked about SFO to LAX, and it's the first thing there. I could get lucky and it's the first thing there. Or I could get unlucky and find out that the SFO list right now is empty because, hey, there's a freak storm, hail, and super high winds where flights in SFO are just grounded right now. There are no flights from SFO to anywhere. So I could get that, we would consider that best case in terms of complexity would be O of 1. It could be the first thing in the linked list, or maybe the linked list is empty. On average, it would be E divided by V. That is the average linked list length. So that would be my average case. So I get to the head of the linked list in O of 1 time, and I traverse its E divided by V average case nodes. All right, so that was one question. What about, I want to know what's the closest other airport to X. So if these represent miles, like I want to leave town, but I don't want to go that far. I just need to get away for a weekend. Or maybe these are, instead of miles, maybe these are dollars. Maybe I just want to leave home and I want to take a flight to somewhere else. What's the cheapest flight if these were dollars? So I want to minimize the number. So if we've got our different representations, we want the worst case, best case, average case complexity. So if I've got an adjacency matrix, then if I want to determine the closest one to SFO or MIA, I would still have to check the whole row. I wouldn't know if the 337 is the cheapest one in the SFO row until I traverse the whole row. So I would have to traverse that whole row to know whether it was the best or not. So worst case would be O of V. Best case would be O of V. Even if the smallest one is first, I don't know it until I traverse everybody in that row. Average case is O of V also. So if the worst and the best are the same, then the average can't be different. All right, what about the adjacency list? In the adjacency list, same situation. The worst case could be O of V because this node could be connected to everybody else. So I'd have to traverse all of them. In the best case, I would find that the linked list is either empty or has only one entry in it. I go to the head of the linked list, I find a 337, and then I see that I go to the next one. Next is a null pointer. I'm done. I get O of 1. I got lucky because the linked list was very short. That was the best case. On average, it would be the same as before, about O of 1 plus E over V. I would have to traverse I always have to traverse the whole linked list. But in the best case, the linked list is size 1 or 0. Worst case, it's size V. Average case, we've got that distribution, E divided by V. The average linked list is about E divided by V in length. Okay, determine if any flights depart from an airport. Okay, so I'm at an airport and I know there's a snowstorm in Detroit this January, and I want to know, can I get to anywhere? You know, I need to get out of town. I just need to get out of Ann Arbor. You know, classes have been really tough, and you know, it's a weekend. I'm going to go somewhere, but I know there's a snowstorm. Is there anywhere I can go at all? All right, well then, in the adjacency matrix, worst case is O of V. I could have lots of infinity symbols in there, and it's only until I get to the last one that I say, okay, there is one flight leaving right now, and that's its cost. So a worst case could be O of V. I would have to look at the whole row before I find something that's not infinity. The best case would be O of 1. I start the LAX row. Hey, there's a number there. I'm done. There is a flight leaving. On the average case, I said O of V here. This one really depends on how dense the graph is. Because if the graph is pretty dense, then I would expect the average to be closer to O of a constant, because there's lots of things. If it's very dense, I would expect, and that's really, if I've got a distance and adjacency matrix, I'd expect it to be dense. Now it could become sparse because of a snowstorm, right? But in general, I would expect it to be somewhat dense, and maybe this could be a constant. But if we think of, well, you know, if there's some infinities, some, not a lot, but some, like we look at the JFK row, it's only half infinities. One of them has to be infinity because it's a simple graph. Of the other 6, half of them are infinity, half are not, and they just happen to be first. So you could argue about this O of V here being, hey, maybe it should be closer to O of 1. It really depends on how dense it is and how and where they are. So even if the graph is half full, it's still pretty dense. But the average row would probably have one in the first few. These last 2 rows are kind of, the JFK row is kind of strange in that the half that are infinities appeared before the half that aren't. Okay, what about for the adjacency list? The worst case would be O of 1. I look at SFO and I say, hey, there's a null pointer here, or there's not a null pointer here. There is not, or there is a place to go. I just need to know, does the linked list head, is it a null pointer or not? So if the worst is O of 1, well, the best can't be any better than that. It can't be better than constant time. And if those are both O of 1, then the average better be O of 1 also. We just have to find, is the linked list empty? Not too bad. Okay, how about another question? If I've got a distance associated with each edge, and I want to associate also not just a distance, but a cost. So I'm going to put 2 values in there. I'm going to put a distance in miles and a cost in dollars, and it says, I want to know how I can determine the greatest distance for the least cost, the best ratio that can be flown from JFK to somewhere else. So I'm leaving New York. I want to go somewhere. I want to go the best number of miles for the number of dollars I spend. So the greatest distance for the least cost. So really what I'm saying is I want the best ratio. So if I do this, I would have to look through each of them and say, hey, what's the ratio of each of these? And then I've got to look at all of them before I know which ratio is the best. So this would actually go back to being the same as our other algorithm where we have to look through everybody. Whoops, sorry. So it would be similar to this one. I don't know if I've got, whoops, not the nonstop flight, which one? Closest other airport, sorry. It would be similar to closest other airport, except instead of the best distance, I would be looking for best ratio, or which would be in fact the highest ratio of miles divided by dollars. So I'd be looking for the highest ratio instead of the lowest miles, but it would still be exactly the same as all of those. Now, what about if I want to know the most efficient route? I want to go from X to Y, and I don't care if there's a layover or 2 or 3, I want to spend the least dollars. So if these numbers represent dollars and I want to get from A to B, I don't care about the stopovers too much. Dollars is my most important aspect. I want to find that flight. Now this gets more complicated. We don't have the algorithm for this yet. So this one is called single source shortest path. So I want to find the shortest path from any vertex to some other given starting point. Now we could do a depth first search. Now a depth first search generally stops when it finds a path, period. So a depth first search would probably find the wrong answer. It's only guaranteed to give the best answer if there's a tree. Now a breadth first search would give the best answer if all weights are considered the same. And really, this is going back to Project 1. Back to Project 1 puzzle solver, if you ran it with a queue and we want to know what's the least number of steps for me to get out, Q would solve that. Because if we consider every cost, every movement to have the same cost, then the least number of steps, because they all have the same cost, the dash dash Q would have actually found us the shortest path. So if there is every edge weight is the same, or we could say that just the number of steps or the total count of steps, then the Q finds it with the breadth first search. Now, if we have weighted edges, then we need, where weights are different, then we need Dijkstra's algorithm. And Dijkstra's algorithm we'll look at later on. We'll look at what is the algorithm, what are the limits, etc. So that'll be a future lecture when we look at Dijkstra's algorithm. So if we look at just a representation here of how depth first versus breadth first search goes, because we put things in the stack, like I say, hey, I started at A and B, and I started at A, and I could add C and B to the stack. Well, whoever gets on the stack last gets taken out first. So B, I say, okay, where can I go from B? I can go to E and D. Well, D comes out first. Where can I go from D? Well, D, I can go to H. Okay, H comes off, and now I've gone to H. And so this is what it means by depth first search. We go deeper and deeper, and we follow a certain path, like northeast, southwest. Let's say there were no buttons and no doors, and we just don't want to go through it. Our depth first search would go like, it would push northeast, southwest, and west would come out first. And then we would push northeast, southwest, while we would push east, because that would be back the way we came. But think about this. Let's say I had a graph where I had a big puzzle, and I had the start is here, and then there's a dot, and then there's the @ sign. Or wait, oh, whoops, I'm thinking of a different project one. @ sign was the starting point. So @ sign was the starting point. There's a dot here, And then there's the goal. Gosh, I can't think of what the goal was in project 1. Let's say dollars. I'm trying to find the dollars. Now, if we did a depth first search, what would happen is we'd add north. So let's call this like 1. So 1 gets added. We can't go east. 2 gets added. Then 3 gets added. And then 3 comes off. And then 3 leads us to 4 and 5 and 6. 6 comes off first and leads us to 7, 8, and 9. 9 comes off and leads us to 10, 11, and 12. We're going west. And we are not going to find that goal. Question mark? Question mark. Yeah, it's been a while. So the question mark. So I can't find the question mark for a long time. I would actually end up exploring everything before I found the question mark. I would explore the entire floor before I found the question mark with a depth first search. The breadth first search, think of the breadth first search explores outward one at a time. It explores everything that's 1 away, and then it explores everything that's 2 away. Because if we think of the queue, we put in the queue everything that's a distance of 0. Then 0 comes out, and we fill the queue with everybody that's a distance of 1. Then we take a 1 out, and we add to the queue everybody that's a distance of 2. Then we take a 1 out, and we add some more 2s. Then we take a 1 out, and we add some more 2s. Then I take a 2 out, and I add things that are a distance of 3 away. And then I take a distance of 2 out, I add something of distance 3, and I go, hey, wait a minute. I found the solution. So the breadth first search goes outward at a distance of 1 each time. It expands its locus of its search outward by 1 every time we finish a distance of 1, we start a distance of 2. And whenever we see a distance of 2, we add things of distance 3, but we never get to the things of distance 3 until we've finished everything at a distance of 2. All right, so when we do depth first search, we're going to find, if the path exists, we will find it. We will find a path that if it exists, it's guaranteed to work. It may not be the shortest. It will work whether it's a directed graph or not. It might be a shortest path, but it's not guaranteed. We could get lucky, but we're not guaranteed to. So if, like in this one, if the question mark had been over here, then depth first and breadth first would have found it and would have provided the same path to get there. And they would have done not quite the same amount of work, but on the order of the same amount of work. And they also would have found the shortest path if it was there. Now, with the depth first search, what we're going to do is we're going to put things on a stack. So I want to know, is there any path from the start S or source S to the goal G? So this is meant to be project 1 generic, where the start and the end could have different characters, or it could be a whole different project 1 entirely, but we still had a start and we still had a goal. So we add the start like SFO to the stack, and then I say, okay, well, I can get there at a cost of 0 because I started there, and then let's keep exploring. So I take that one off, that becomes where I am, and then I add the things that I can reach from there. Boston at 2704, Orlando at 1846, DFW, Dallas-Fort Worth at 1464, 1, 2, 3, I think I've got one more. Yep, LAX at a distance of 337. And why did I add them in that order? Because that's the order I saw them. For whatever reason. Maybe that's the order they were listed in the adjacency list. That just happens to be the order that we visited them. So then we would take, if we were trying to get to a different place, then LAX would come off. It would become our current location. So this one isn't our current location anymore. LAX is, and then from there we could add Miami, and that's all. So we take Miami off, and I'm trying to get to New York, for instance. I take out Miami, and I add things that I could reach from Miami that I haven't already reached. So I'd add JFK to that, and then JFK comes off. We say, hey, JFK, that could be my goal, and now I've got my total. I'd have to keep a running total somewhere, and that's my total cost. Now, maybe there's a shorter way to get there, maybe not, but that's the one I found given this depth first search. So depth first search says, we're going to make sure that we don't loop forever. We're going to mark the source as visited, we're going to push it to the stack, and while the stack's not empty, it says we're going to get and pop the top candidate from the stack. For every child, we're going to check if it's unvisited. And by every child, we mean for every thing adjacent. We could also say for every node adjacent to the candidate would be the same thing. So for every node adjacent to the candidate, we check if it's unvisited, we mark it as visited, we push it to the top of the stack, and we check if it's the goal. So this algorithm is checking for the goal as we pop it rather than as we push it. So if we checked as we push it, we might make it more efficient, a little bit more efficient in some cases. So, but that is guaranteed to find us our goal. And here's an example of running it. So I've got, I'm trying to discover a path from A to E. And I'm going to use depth first search. We've got the discovered vertices, so things that are, what is that, greenish? Greenish is the ones we've discovered. The blue is the ones we haven't yet discovered. The light edges are the ones we haven't explored. The black ones, the dark black ones with an arrow, are the ones we have discovered. And the blue dotted ones, the back edge is basically saying, hey, I discovered a way to get back to somewhere I've already discovered, and those back edges really aren't important to me. They're redundant paths. Okay, so I start out and I add A, then I take out A and I say, well, what can I get to from A? I add B to the stack, and I add C to the stack, I add D to the stack. Those all get added to the stack. Then there's nowhere else to go from A, so I have to take off of the stack, and D becomes my current location. Well, D, I don't discover anything new. I discover A, oh, A is already discovered. I can get to C, C's already discovered. Those edges weren't important, so we don't add anything to the stack. We have to go and take someone else off the stack. C becomes my new place to investigate. From C, I say, where can I go from C? Well, I could go to for A is already discovered. I could go to D, D's already discovered. I could go from C to E is not yet discovered. I add E, and then I would take E off of the stack and discover that E is where I wanted to end up. Okay, so depth first search with an adjacency list, we're going to, it says called. It means we're going to perform. We're going to check each vertex at most once. We're not going to put things into the stack more than once, which means they won't come out more than once. So when it says called, it basically means each vertex will be the current location at most once. For example, in the previous one, B never became our current location. It got added to the stack, but it didn't get used. And maybe, let's say, if, whoops, sorry, go back one. What if there had been another one, B is connected to F, and that's the only way to get to F? Well, maybe F never even gets into the stack. B got into the stack, but it never came out. F never got added to the stack at all. So every vertex is visited at most once. Some might be visited 0 times. The adjacency list for each vertex is visited at most once because because we never take anything out more than once, we never have to look through its adjacency list more than once. So the adjacency list for each vertex is visited at most once because vertices become the current vertex at most once. So then if we visit each vertex at most once and we traverse its adjacency list when we visited it, then our complexity would be O of V plus E. It would be linear in the number of vertices plus edges. Now, what if it was an adjacency matrix? Well, then we're still going to visit each vertex at most once. Each vertex will come out of the stack and become the current vertex at most once. But every time we do, we've got to go through that whole row, all O of V of them, which means it's O of V squared, which means it's quadratic with the number of vertices. Now, wait a minute. Doesn't that mean that if it's an adjacency list, it's just faster? Why would we ever represent it as an adjacency matrix? Well, remember, if we're doing an adjacency list, E is proportional to V if it's a sparse graph. So let's look at this. If it was sparse and it was an adjacency list, what if it was dense and we represented it as an adjacency list anyway? Well, if it's sparse, then E is proportional to V, and this is just O of V plus E is the same as saying O of V plus V, which is O of V. All right, but over here, E is proportional to V squared, which means we've got O of V plus V squared, which is O of V squared. So it's not the representation that makes the adjacency list more efficient. It's the fact that it was sparse and we chose an adjacency list. If it was sparse and we did a distance matrix, it would still be O of V squared. Once it's an adjacency matrix, it's going to be O of V squared. But if it's sparse and we use the list, we could get O of V plus V, which is just O of V. So it's not the representation that makes it, it's the right representation for that graph that could make it more efficient. Okay, breadth first search. So when we do a breadth first search, we're given an unweighted graph. We want to discover the shortest path from a start to a goal, if any exists. And we're going to use a queue. It works on graphs, it works on directed graphs. It will discover a shorted path either on an unweighted graph or if all edges have equal weight. They're synonymous. If I just say, hey, all the edges are of weight 1, well, then that's the same as all being unweighted, and I just want the number of steps that it's going to take. So breadth first search will find the shortest if it's an unweighted or every cost is the same. And so here, because of the graph, we're showing this, it looks like a stack, but really we're showing it with a queue with the front being at the bottom. So it's just that vertical representation was all that would fit on one slide and still have the map there. So we add our starting point. So I'm trying to get from, say, SFO to JFK. So I add SFO, add a distance of 0, and I take it out, and I add things in. Boston at 2704, Orlando at 1846, DFW at 1464, and then I take out BOS. Whoops, sorry, LAX. I wasn't quite done. I forgot it was the fourth one. So I add LAX. Then we take out Boston at 2704, comes out of the queue. And then I say, okay, well, I can go to MIA, and I can go to JFK. And then if we keep track of and stop when we add the goal, then we could stop right here and say, hey, I just added JFK, that's my goal. I don't have to wait until I take it out. So if it really depends on how we write the algorithm. So, and then we get a total of 2891, which I believe is cheaper than the other one we had done. Now it really comes down to when we check this. So it's stated here in the slides, we listed it as we push it. So as we push it, we're going to test it. We don't wait until it comes out to say, hey, is the one that I took out the goal? It really comes down to, is it the goal when I push it? So if we did it differently, we'd get a different efficiency. And I think I misstated that on the other one. It is, we are in fact checking as we push. The one that we push the goal, then let's stop. Let's not wait until it comes out. So this is basically the same as the other one, except we say Q and back and front instead of stack and top. So we push to the back of the Q and we take it from the front if we need to get one. And here's a slightly different graph with a slightly different example. So we're using breadth first search and we want to discover if a path exists from A to F. And what we've got is here the L0 and L1 is basically marking our how far are we from the beginning. How many edges have we had are checked in our path. So we start with a distance of 0, we add A to the Q, and then A comes out of the Q and becomes our current, and we start exploring things that are a distance of 1. So B at a distance of 1 gets added, C gets added, D gets added. We've added everyone who's a distance of 1 step away from the start. And then we start taking B out. So we take something of distance 1 out, and we say, well, where can I go from B? Well, I could go back to A, already discovered. I could go to C, it's already discovered. Those back edges aren't useful, so we don't add anyone to the Q. Then I say, wait, B could get me to E. Let's add someone who's a distance of 2 to the Q. And the blue sort of dotted box, I think that's blue. The dotted box there around CDE is showing us what's in the queue. CDE are what's in the queue right now. So then I take C out. C becomes my current location. I say, where can I go from C? And let's assume that we just visit in alphabetical order. So C can go to A, already discovered, can go to B, already discovered, D, already discovered, E, already discovered. None of those are useful for me. It can also go to F, which is not yet discovered. So I add F to the queue, and I say, hey, wait, whoops, forgot there wasn't another animation for that. I say, wait, F was my goal. I've just added the goal to the queue. I'm done. I stop now because I've added my goal to the queue. So we just got a few more slides here. We're almost going to finish on time today. So breadth first search, we're going to be taking every vertex out of the queue and making it the current location at most once. Some will get added and never removed. Some will never get added at all. So we're going to do this for each vertex at most once, and for each one we have to visit it. If once we take it out, we have to visit its entire adjacency list, which is 1 plus E over V. So the total algorithm would be V times 1 plus E over V is O of V plus E, same complexity as the DFS. For the adjacency matrix, same complexity as before. No difference in the complexity. It's just which path does it find. And this is the worst case complexity, right? This is if we had to visit everything before finding it. We could get lucky. We could start out with I start the starting point, I take it out, I visit one thing, there it is, I'm done. And that could happen with either one. So this is really what we've been showing is the worst case analysis here. In the worst case, they could both take up to V squared to discover, hey, the goal was, I had at over here, and over in the corner I had number sign dot number sign question mark, and that was the edge of the map. So both of them had to explore almost everything before discovering there's no way to reach the target. Now, Dijkstra's algorithm, which, like I said, we're going to come back to Dijkstra's algorithm in a future lecture. Dijkstra's algorithm is going to discover the shortest path from the start to the goal, even if the edge weights are not all the same. And so that could be, there's restrictions on it. There's another restriction we're going to have to add when we do Dijkstra's. But assuming we meet that restriction, it will find the shortest path. And the restriction isn't a huge one. The restriction is just there can't be any negative edge weights. So it makes sense. There usually isn't a plane from, if there was a plane trip from Ann Arbor to Detroit and they paid you money to do it, lots of people would be taking that flight. So generally that doesn't happen in the real world, so it's not going to be a terrible restriction on Dijkstra's algorithm. So just summary slide, we've got the background and definitions, bunch of those. How do we represent our data? How do we represent our graph? What can we do with our graph? And then we'll have Dijkstra's in an upcoming lecture. Okay, so we're done. Only 1 minute over today. All right, I'm going to get some lunch, and I'll see people in office hours later.